Welcome. Now we will explore magnetostatics and the Lorentz force. These concepts help us to understand how magnetic fields affect electric charges. Let us start with the magnetic field. This is a area around a magnetic dipole or a wire carrying current where we can feel magnetic forces. These forces can either attractive forces or repulsive forces. Intensity of magnetic field. Now the intensity of the magnetic field is simply the strength of this field. It is defined by the force acting on a unit north pole placed at a point inside the magnetic field. Magnetic induction, often represented as B, is a vector quantity. It tells us both how strong the magnetic field is and which direction it is pointing. We define it as the number of magnetic lines of force passing through a unit area. Magnetic lines of force. These are imaginary lines that shows us the direction a north pole would move if we placed it in the magnetic field. They help us visualize how magnetic field behaves. We can visualize magnetic fields using these magnetic lines of force. These lines always form closed loops and never cross each other, which is a very important characteristic. Also, when these lines are closer together, it means the magnetic field is stronger in that area. That is, the density of lines indicates the strength of the magnetic field. Next, let us talk about magnetic flux, denoted as phi. This is the total number of magnetic lines of force passing through a specific area. To calculate it, for a small area dA with a magnetic field B at an angle theta, we use the formula d phi is equal to B dA cos theta. For a uniform magnetic field and a surface area A, the magnetic flux can be expressed simply as phi is equal to B dot A. Magnetic induction B. Magnetic induction, which we can think of as the strength of the magnetic field, is defined as the magnetic flux per unit area. B equal to phi divided by A. Remember, the SI unit of magnetic induction is the Tesla. 1 Tesla is equivalent to 1 Weber per square meter. A moving electric charge creates both an electric field and a magnetic field. This is a very fundamental concept in electromagnetism. According to Ampere's circuit law, the magnetic field around a wire carrying current depends on the amount of current flowing through the wire. It is directly proportional to the current and inversely proportional to the distance from the wire. To find the direction of the magnetic field around a straight wire, we can use the right hand rule. If you point your thumb in the direction of the current, your fingers will curl in the direction of the magnetic field lines. The magnetic force acting on a moving charge can be expressed as Fb is equal to Q into V cross B, where Q is the charge, V is its velocity and B is the magnetic field. This force is always perpendicular to both the charge's velocity and the magnetic field. So it doesn't change the speed of the charge, just change its direction. The magnitude of the magnetic force is given by Fb is equal to QVB sin theta, where theta is the angle between the velocity and the magnetic field. If the charge moves parallel to the magnetic field, then the magnetic force is 0. This means the force only acts when the charge moves across the field lines. Now let us discuss the Lorentz force, which is the total force acting on a charged particle due to electric and magnetic fields. The formula for Lorentz force is F is equal to Q into E plus V cross B. Here E is the electric field and B is the magnetic field. The electric part of the force acts in the direction of the electric field and can cause the charge to speed up. In contrast, the magnetic part acts perpendicular to both the velocity of the charge and the magnetic field direction, which changes the charge's path but not its speed. In a uniform magnetic field, a charged particle will feel a constant magnetic force that is always perpendicular its velocity. This results in the particle moving in a circular or helical path. Whether it goes in a circle or helix depends on how its initial velocity relates to the magnetic field. The radius of the circular path can be calculated with the formula R equal to mv divided by qb, where m is the mass of the particle, v is its speed, q is its charge, and b is the magnetic field strength. There are some important points to remember about the Lorentz force. First, the magnetic force is zero if the charge is stationary or if it moves in the same direction as the magnetic field. Second, the force is maximum when the charge moves perpendicular to the magnetic field. This results in the most deflection of the particle. Finally, the work done by the magnetic force is always zero because the force acts perpendicular to the particle's motion. This means that magnetic fields can change the direction of a charge but not its speed. In this diagram, we can see how positively and negatively charged particles move in a uniform magnetic field that is directed out of the screen. The magnetic force causes the particles to follow curved paths. This curvature depends on whether the particle is positively or negatively charged and the direction of the magnetic field. For instance, positively charged particles curve downward while negatively charged particles curve upward, as shown in the diagram. To summarize, the Lorentz force is a key concept in electromagnetism. It combines the effects of electric and magnetic fields on moving charges. Understanding the Lorentz force helps us explain how charged particles behave in different physical situations, such as in particle accelerators and natural phenomena like auroras. Thank you for your attention.